Welcome to Oddly Real. I'm Nem Stefanovic. Many of us are familiar with our local star, the Sun, and the planets in our solar system. But how familiar are you with the stars and planets that neighbor our solar system? In fact, there are actually quite a few that are not very far from us at all within our galaxy. It's commonplace that stars also have planets of their own. It's only within the past few decades, roughly speaking, this generation of humans, that we have actually confirmed the existence of extrasolar planets or exoplanets. In fact, there are now thousands of confirmed exoplanets and many more that are in the process of confirmation, or yet to be discovered around candidate stars. There are actually far too many exoplanets and stars to comprehensively discuss, even within a few light years of the Sun. However, we can restrict our attention to some interesting stars and exoplanets in our immediate vicinity within about 15 light years. Our Sun is located within the Milky Way galaxy. Our galaxy is considered one of typical size in the universe, containing somewhere between 100 and 400 billion stars. The Milky Way's structure consists of just two major spiral arms, which are made of stars, gas, and dust. The major spiral arms are called Scutum Centaurus and Perseus, which are attached to the ends of an elongated galactic bar at the center of the galaxy. These spiral arms have high densities of both old and young stars. There are also two minor arms located between the major arms called Norma and Sagittarius. The minor arms contain gas and areas of star-forming activity. Our Sun is near a small partial arm called the Orion Arm, located between the Sagittarius and Perseus arms. Our Sun orbits the center of the Milky Way galaxy at a velocity of 828,000 kilometers per hour, or 230 kilometers per second. The Sun makes a complete orbit around the galaxy every 230 million years. Our own Sun is considered an average-sized star. It's estimated to be about 4.5 billion years old, with the Earth located 150 million kilometers from it. Our Sun is around 100 times wider than the Earth, but its volume could contain 1.3 million Earths. One day, the Sun will run out of its nuclear fuel, and when it does, it will expand into a red giant star. This is expected to take place in another 5 billion years. In fact, the Sun will grow so much that it will engulf the inner planets up to the Earth. Eventually, the Sun will eject its outer layers, leaving a white dwarf star, which will be about the size of the Earth, but with the mass of a star. We classify stars according to their temperature and color. The brightest of stars relates to their energy output and their distance from the Earth. Hotter stars tend to look more blue or white, whereas cooler stars tend to look orange or red. The star classification scale ranges from O-type stars that are hotter and look blue, down to M-type stars that are cooler and look red. The more massive the star, the shorter its life, since its nuclear fuel is consumed faster. There are also other types of stars that aren't included here, like supergiants, red giants, and white dwarfs as examples. That's because the star classification is for main sequence stars, which are actively fusing hydrogen into helium for energy, as opposed to other stages in a star's life cycle. Our own star is classified as a G-type yellow star. You might have heard that the Sun is not actually yellow in color, but white. This is indeed true, since the Sun radiates light across the entire electromagnetic spectrum, which in aggregate would be white. However, the actual color we perceive as human beings can be complicated, since it depends on the refraction of light through Earth's atmosphere, the sensitivity of our own eyes to certain colors, and various other factors too. We'll keep things simple here and stick to the color classification system without worrying about the actual perceived colors. Perhaps one of the most stunning discoveries in science over the past few decades is that exoplanets, or planets outside of our solar system, are confirmed to exist. There are now close to 6,000 confirmed exoplanets, with many more as candidates awaiting confirmation. More are being discovered regularly. The implications of this are extraordinary, since not only do exoplanets exist, but they appear to be prevalent throughout our galaxy and very likely beyond. There is also a classification system for planet types. Terrestrial planets are rocky or metallic at their core. These are smaller than Earth and may have oceans or atmospheres as well. Super Earths are also rocky, but they are more massive, between the size of Earth and Neptune. Neptune-like planets are the size of Neptune or Uranus, with atmospheres that are mostly made of hydrogen or helium. These planets may also have rocky or metallic cores. Gas giants are massive planets like Saturn or Jupiter, or even larger. These are mostly composed of helium or hydrogen gas that is swirling above a dense core. There is also an unknown type planet classification for planets that may not fit into any of the other classes. One particularly interesting prospect for exoplanet search is finding planets that are within a star's habitable zone. The habitable zone is a region around a star where the conditions are just right to allow for water to exist in liquid form on the planet's surface. Why is liquid water so important? It appears to be an essential ingredient for life. Currently, our only reference for the evolution of life is here on Earth. Earth is around 4.5 billion years old. Human beings have only been present for over the past 200,000 years, which is very recent in that timeline. It is estimated that our planet will only remain habitable for another 1 billion years before the sun's temperature increases enough to completely dry out the Earth. Stars like our sun, or G-type yellow stars, are actually relatively short-lived compared to the timescales that life needs to develop to produce beings of higher intelligence. However, slightly cooler and longer-lived stars like K-type orange stars may be much more suited for advanced life. Those stars live for tens of billions of years to allow for evolutionary development. Additionally, there are 3 times the number of K-type stars compared to G-type stars like our sun within the galaxy. One interesting thing to note, however, is that less massive and cooler stars have a narrower habitable zone around them. For example, red dwarf stars, or M-type stars, have very narrow habitable zones that are very close to the star, which would expose any planets there to extreme levels of X-ray and UV radiation. These planets could receive radiation that is 100,000 times more intense than what Earth receives from the sun. However, these types of stars also have longevity and last for over 100 billion years. We will explore our local stellar neighborhood up to 15 light years from our sun. The closest star system to us is Alpha Centauri, which is approximately 4.3 light years away, visible in the southern hemisphere. It's actually a triple star system, with stars Rigel Kentaurus, Ptolemy, and Proxima Centauri. Rigel Kentaurus is a G-type yellow star that is larger than the others. It has a similar mass and temperature to our sun, but about 25% larger. It's an older star that shines brighter. Rigel Kentaurus is in the binary orbit with its neighbor star, Ptolemy, at a distance that is slightly greater than the distance between the sun and Uranus. Ptolemy is a K-type orange star with half the power output of the sun. It has almost the same mass as the sun, but is slightly smaller. The binary pair of stars appears as the third brightest point beyond our solar system. Finally, Proxima Centauri is the third star in the system and technically the closest star to us at 4.25 light years. It's an M-type star, so smaller and fainter, with a mass that is 1/8 of our sun and has a radius that is 1/7 the size. The interesting thing about our nearest neighbor star is that it has a confirmed exoplanet, Proxima Centauri b, and that exoplanet is within the habitable zone of the star. The planet is classified as a super-Earth, being just slightly more massive than the Earth and potentially rocky. It orbits the star every 11.2 days. However, Proxima Centauri is an active red dwarf, meaning it exhibits flares and high-energy bursts of X-rays and UV rays. High-energy ultraviolet radiation can ionize atmospheric gases, if they exist on the planet, to produce charged particles that have the energy to escape the planet's gravity out into space. This may strip away any atmosphere on the planet. Calculations show that Proxima Centauri b would lose an atmosphere as thick as the Earth's within 100 million years. Barnard's star is an M-type red dwarf that is located almost 6 light-years away. It is 1/6 the mass of our Sun. Yet here, there are already 4 confirmed exoplanets, Barnard B, C, D, and E. They are all terrestrial, rocky planets that are less massive than the Earth, ranging from 1/5 to 1/3 of our planet's mass. They orbit their star in a relatively short time, having orbitals ranging from 2.3 days to 6.7 days. One of my personal favorite nearby star systems, mostly because of references in pop culture, is Wolf 359, which is located 7.9 light-years away. It has the interesting property that it is a red dwarf star with a mass only 0.09 times that of our Sun, making it one of the least massive stars that's been discovered. This is a very active star, producing flares every 2 hours on average. However, a super flare also occurs about 10 times per year, making the star appear 10 times brighter. It's not clear why there is such enhanced activity, although there are speculations that it's either due to the star's fast spin, rotating once every 2.7 days, or it's a result of interactions with unconfirmed exoplanets. Lalande 21185 is an M-type star located 8.3 light-years away, with a brightness that is 200 times dimmer than our Sun. It has 2 confirmed exoplanets. The first is GJ411b, a super-Earth that is 2.69 times the mass of the Earth with an orbital period of 12.9 days. The second exoplanet is HD 95735c, which is a Neptune-like planet with a mass of 13.6 times that of Earth's. It orbits further out with an orbital period of 8.1 years. One interesting aspect about this star system is that it is getting nearer to our solar system, such that in 20,000 years, it'll be only 4.65 light-years away. It is interesting to note just how many additional nearby stars have confirmed exoplanets. Specifically, Epsilon Eridani, GJ887, Struve 2398, Groombridge 34, Tau Ceti, and many others. It's very apparent that exoplanets are commonplace. We'll round out this guide by focusing on a few more star systems that contain exoplanets in their habitable zones. Ross 128 is an M-type star located 11 light-years away with an exoplanet, Ross 128b, located within the habitable zone. This planet is a super-Earth with a mass 1.4 times the Earth's and an orbital period of 9.9 days. This red dwarf is interesting since, unlike many active red dwarf stars, it seems to be far quieter, meaning that there aren't as many flares and there may be far less radiation exposure. The exoplanet only receives 1.38 times more irradiation than our Earth. Ross 128b is estimated to have temperatures between minus 60 degrees Celsius and plus 20 degrees Celsius, which is actually around room temperature. This is partly due to the cooler nature of the star, which has half the surface temperature of our Sun. Ross 128 is on a trajectory to bring it closer to our solar system. It is expected to be our nearest neighbor star in 79,000 years. GJ1061, or Gliese 1061, is an M-type red dwarf star that is 12 light-years away. It's an older star at around 7 billion years, but it's also relatively inactive, which makes it more suitable to support life. It has 3 confirmed exoplanets. Gliese 1061b, C, and D. Gliese C and D are both located in the habitable zone, and each planet is about 70% more massive than the Earth. They also orbit the star quickly at 6.7 days and 13 days respectively. Gliese D is particularly interesting since it receives a similar amount of energy from its star as the Earth receives from the Sun. This means liquid water would be permissible on the planet's surface and the temperature would be similar to the Earth's. Teegarden star is an M-type star located 12.5 light years away with a very small mass and radius approximately 1/10 of that of the Sun. There are 3 confirmed exoplanets here, Teegarden B, C, and D. Both Teegarden B and C are in the habitable zone. Both are super-Earths with masses slightly larger than the Earth. Teegarden star has relatively low activity compared to other late M-dwarf stars, which improves its chances to support life. Finally, Wolf 1061 is an M-type star located 14 light-years away. It has 3 confirmed exoplanets, Wolf 1061b, C, and D, with C being in the habitable zone of the star. Wolf 1061c is a super-Earth that is 3.41 times more massive than our Earth and has an orbital period of 17.9 days. Analysis suggests that high temperatures there could be causing a runaway greenhouse effect to produce excessive water evaporation if water is indeed present. There is a similar situation that has occurred on Venus. Additionally, since Wolf 1061c's orbit varies much quicker than Earth's, there would be very chaotic climate changes resulting in fast transitions from warm phases or ice ages. We've only just scratched the surface of stellar and planetary exploration around our sun. The galaxy is an enormous place with lots more to discuss, but we'll leave it here for now. I hope you enjoyed this episode, and remember, oddly real, really interesting.